It's a crisp January morning at Kennedy Space Center. The air temperature hovers just above freezing as technicians make their final preparations. 7 crew members climb aboard Space Shuttle Challenger for what should be a routine mission. Among them is Krista McAuliffe, a high school teacher from New Hampshire who captured the nation's heart. Millions of children across America are watching from their classrooms, excited to see their first teacher venture into space. The countdown proceeds normally. Systems check out green across the board. At 11:38 a.m. Eastern Standard Time, the solid rocket boosters ignite with thunderous force. Challenger lifts off from Launch Pad 39B, climbing steadily into the brilliant blue Florida sky. For the first minute, everything appears nominal. The shuttle rolls through its programmed flight path as it has done 24 times before. But 73 seconds after liftoff, something goes catastrophically wrong. A brilliant flash erupts from the external tank. The shuttle disappears in a massive cloud of vapor and debris. Pieces of the vehicle tumble through the sky, leaving twisted trails of smoke against the azure backdrop. In classrooms nationwide, children watch in stunned silence as their dreams of space exploration turn to horror. This is the story of how a series of critical decisions, engineering compromises, and communication failures led to one of the most devastating accidents in the history of human spaceflight. To understand what happened that morning, we need to go back to the beginning of the Space Transportation System program. In the early 1970s, NASA envisioned a revolutionary spacecraft that would make access to space routine and economical. The space shuttle would launch like a rocket, operate in orbit like a spacecraft, and land like an airplane. It promised to reduce the cost of reaching orbit while providing unprecedented capability for deploying satellites, conducting experiments, and building space stations. The shuttle system consisted of 3 main components working in perfect harmony. The orbiter itself housed the crew and cargo bay. 2 solid rocket boosters provided the initial thrust needed to escape Earth's gravity well. The massive external tank carried the liquid hydrogen and oxygen fuel that fed the orbiter's main engines during ascent. Those solid rocket boosters were engineering marvels in their own right. Standing over 149 feet tall and weighing more than 1.3 million pounds when loaded with propellant, each booster generated 2.6 million pounds of thrust. Unlike liquid fuel rockets that can be shut down if problems arise, solid rockets burn continuously once ignited. There's no stopping them until the fuel is exhausted. The boosters were manufactured by Morton Thiokol at their facility in Utah. Due to transportation constraints, each booster had to be assembled from multiple segments that were joined together at Kennedy Space Center. The joints between these segments were sealed using rubber O-rings, designed to prevent the escape of hot gases during flight. This joint design had been a source of concern since the early days of the shuttle program. Engineers knew that the joints experienced significant stress during ignition and flight. The immense pressure and vibration caused the metal casings to flex and deform slightly. The O-rings had to maintain their seal even as the joint geometry changed dynamically throughout the flight. During previous missions, technicians had discovered evidence of hot gas blow-by past the primary O-ring seals. Soot and heat damage on recovered booster segments revealed that the sealing system wasn't working as originally intended. In some cases, the secondary O-ring had prevented catastrophic failure, but this backup system wasn't designed to be the primary means of sealing the joint. Morton Thiokol engineers became increasingly worried about the reliability of the joint design, especially under certain conditions. Temperature emerged as a critical factor affecting O-ring performance. The rubber compounds used in the seals became less flexible as temperatures dropped, reducing their ability to respond quickly to joint deformation during ignition. Laboratory tests confirmed these concerns. At lower temperatures, The O-rings took longer to seal properly and were more likely to allow initial gas blowby. The engineers established a minimum temperature recommendation based on their analysis of flight data and test results. As 1986 began, NASA faced intense pressure to maintain an ambitious launch schedule. The agency had promised frequent shuttle flights to justify the program's cost and complexity. Delays were costly and embarrassing, especially with so much public attention focused on the Teacher in Space mission. The original launch date for Mission 51L was set for January 22nd, but technical problems and weather delays pushed the flight back repeatedly. Each postponement brought more scrutiny from Congress, the media, and the public. NASA managers were determined to get Challenger off the ground as soon as possible. On the evening of January 27th, weather forecasters predicted overnight temperatures would drop well below freezing at the launch site. Ice was expected to form on the launch pad and vehicle surfaces. These conditions raised immediate concerns among the Morton Thiokol engineering team. The engineers knew that cold weather could severely compromise O-ring performance. They had data showing that previous flights launched in cool conditions experienced more severe joint heating and blowby. With overnight lows predicted to reach the mid-20s, the temperature would be far below anything the shuttle had experienced during launch. A series of teleconferences were hastily arranged between Morton Thiokol, NASA Marshall Space Flight Center, and Kennedy Space Center. The discussions would prove to be among the most consequential engineering meetings in aerospace history. Morton Thiokol's engineers presented their analysis showing that low temperatures significantly increased the risk of O-ring failure. They argued that the correlation between temperature and joint heating was clear from flight data. The primary O-ring might not seal properly in the predicted conditions, placing complete reliance on the secondary seal. The engineering team recommended postponing the launch until temperatures rose to at least 53 degrees Fahrenheit. This recommendation was based on the lowest temperature at which they had previous flight experience without severe heating problems, but NASA managers pushed back hard against the delay recommendation. They questioned the engineering analysis and demanded more definitive proof that cold weather would cause a failure. The pressure to launch was enormous, and another delay would be difficult to explain to senior NASA leadership and the public. The teleconference stretched late into the evening as engineers and managers debated the risks. Charts and data were transmitted between locations as each side made their case. The Morton Thiokol engineers stood firm in their recommendation, but they faced intense questioning about the validity of their conclusions. What happened next would haunt everyone involved for the rest of their lives. As the debate intensified, Morton Thiokol management found themselves caught between their engineers' warnings and NASA's demands for launch. The company's senior executives requested a 5-minute offline caucus to discuss their position internally. What transpired during those crucial minutes would fundamentally alter the trajectory of the space program. Away from NASA's listening ears, Morton Thiokol's management team huddled to weigh their options. The engineers continued to advocate for their temperature concerns, presenting additional data that showed clear patterns of joint distress in cooler conditions. But the business implications loomed large. Morton Thiokol held a lucrative contract worth hundreds of millions of dollars, and challenging NASA's launch schedule could jeopardize future relationships. The company's vice president of engineering found himself in an impossible position. His technical team was unanimous in their assessment that launching in such cold conditions represented an unacceptable risk. Yet the pressure from both NASA and his own management to reconsider was immense. The engineers had done their job by identifying the hazard, but the final decision rested with those who balanced technical concerns against programmatic pressures. When the teleconference resumed, Morton Thiokol delivered a stunning reversal. Despite their engineers' objections, management announced they were withdrawing their recommendation to delay the launch. They would support proceeding with the mission as scheduled. The decision sent shockwaves through the engineering team, who had never seen their technical judgment overruled so decisively. NASA managers accepted the revised recommendation with apparent relief. The launch would proceed as planned, pending resolution of ice concerns at the pad. Few participants in that fateful teleconference could sleep well that night, knowing the weight of the decision they had collectively made. Meanwhile, at Kennedy Space Center, technicians worked through the frigid night to assess ice conditions around the launch pad. Temperatures plummeted even lower than predicted, reaching a bone-chilling 18 degrees Fahrenheit just hours before the scheduled liftoff. Ice formed thick coatings on service structures, pipes, and the shuttle's external surfaces. The ice inspection team discovered conditions unlike anything they had previously encountered. Massive icicles hung from the launch platform like frozen daggers. The shuttle's surfaces were covered in a crystalline coating that sparkled in the floodlights. Water systems had frozen solid, creating additional hazards for ground crews. Despite these extraordinary conditions, NASA's ice team determined that the accumulation posed no unacceptable risk to the vehicle during launch. Their primary concern focused on ice breaking free and potentially striking the shuttle during ascent. The frozen O-rings buried deep within the solid rocket booster joints received no specific evaluation or consideration. As dawn broke over the Space Coast, the launch team began their final preparations. The 7 crew members completed their traditional breakfast and suiting procedures, unaware of the heated debates that had raged through the night. Commander Dick Scobie and his crew trusted implicitly in the thousands of engineers and technicians who had declared their vehicle ready for flight. The weather gradually improved as morning progressed, but temperatures remained well below normal launch conditions. Ice continued to coat various systems, requiring additional inspections and evaluations. Each delay pushed the launch time later into the morning, but mission managers remained committed to getting Challenger off the ground that day. Television networks prepared for extensive coverage of the historic Teacher in Space mission. Krista McAuliffe had captured public imagination with her enthusiasm and dedication to inspiring young people about space exploration. Students across the nation gathered in gymnasiums and classrooms, many seeing a shuttle launch for the first time. The crew access arm retracted from the orbiter at 8:36 a.m., signaling the beginning of the final countdown sequence. Liquid hydrogen and oxygen flowed into the external tank as the shuttle's main engines prepared for ignition. The solid rocket boosters awaited their moment to unleash their devastating power. At T-9 minutes, the countdown entered its planned hold to allow for final systems checks and weather evaluation. Ice teams completed their last inspection of critical areas around the vehicle. Launch controllers verified that all systems showed green across their monitoring displays. The hold was lifted, and the final 9 minutes of countdown began. Challenger's crew performed their last-minute checks while ground controllers monitored hundreds of parameters. The shuttle's computers took control of the final seconds, ensuring precise timing of the complex ignition sequence. At exactly 11:38 a.m. Eastern Standard Time, the solid rocket boosters erupted to life with a thunderous roar that shook buildings miles away. Challenger rose majestically from the launch pad, climbing through the clear morning sky on a pillar of flame and vapor. For those first critical seconds, everything appeared perfect. The shuttle rolled through its programmed flight path as telemetry data flowed normally to mission control. But deep within the right solid rocket booster, events were already unfolding that would doom the mission and its crew. The Challenger disaster stands as a stark reminder of how organizational pressure can override engineering judgment with catastrophic consequences. 7 brave souls perished that cold January morning because critical voices were silenced and warning signs ignored. The Rogers Commission investigation would later reveal the full extent of communication breakdowns and flawed decision-making that led to this tragedy. In the aftermath, NASA implemented sweeping changes to its safety culture and decision-making processes. The agency learned that schedule pressure must never supersede crew safety, and that engineers' concerns required genuine consideration rather than bureaucratic dismissal. The Space Shuttle program would eventually resume, but it carried forever the lessons written in the smoke trails over Cape Canaveral. Today, as we venture toward Mars and beyond, the Challenger crew's sacrifice continues to guide our approach to human spaceflight. Their memory reminds us that exploration demands not just courage from those who fly, but wisdom from those who send them. The stars they sought to reach remain our destination, illuminated now by the knowledge gained from their loss.